In this video, I'm going to do three examples of showing a series are convergent or divergent, and talk about what test I use in each case and why. So let's look at A. First off, we have this series from 3 to infinity of 2 over the square root of k minus 2. This is going to be very similar to the series from k equals 3 to infinity of 2 over square root of k, which we know diverges by a p-series. So, one thing I might try here is a limit comparison test. Limit comparison test says I do 2 over square root of k minus 2 over 2 over square root of k. And you don't really even need the 2 in there. You could have done 1 over square root of k. So let's go ahead and change it to that just because I want you to see. Because we know 1 over square root of k. We know that's divergent by p-series. Okay, just a little note there for myself. And I'm going to take the limit as k goes to infinity. This goes to a non-zero finite number. It tells me they both either diverge or converge. First thing I do is flip and multiply. So I have the limit as k goes to infinity of 2 times square root of k over square root of k minus 2. And what I'll do on this one, you could use L'Hopital's, but I think what's going to be easier is to write everything under the radical, pull the 2 out front. Doesn't depend on k, so limit is k goes to infinity, square root of k over k minus 2. In fact, if you want, I'm not going to do this step, you could put the limit inside the radical. K over k minus 2 goes to 1, so this goes to the square root of 1 times 2 is 2. That's a non-zero finite number. So we know this first one diverges, and I use the limit comparison test. Always should mark which test. I know this sheet's going to get a little messy, but it's because I'm doing a few of them at once. The second one, always look at what's going on with your sequence, because check this out. If I do the limit as k goes to infinity of k over 1 plus 2k, if I use one round of L'Hopital's, I get the limit as k goes to infinity of 1 over 2, or 1/2. That does not equal 0. We're already done on this one. It's divergent by the test for divergence. I'm just going to call it the divergence test. Remember, if that sequence piece does not go to 0, you're done. There's no way it can converge, and that goes for alternating series too. Last one, what I would look at is the lead terms, because I got a rational expression in there, and I see the 2k squared over k cubed. So the series I might choose to compare this to is going to be the reduced form of that, 1 over k. Again, I'm not going to worry about the constant. It's not going to make a big deal. As k goes from 0 to infinity, we know this diverges by p-series. So I'm going to do another limit comparison test. I like that better than the regular comparison test. I think it's a little quicker, but they both have their advantages and disadvantages. So if the limit is k goes to infinity, we'll put this guy on top, 2k squared plus 1 over k cubed plus k plus 1, all over 1 over k. So we're going to flip that bottom guy and multiply, so the numerator is going to get multiplied by k. So we have the limit as k goes to infinity of 2k cubed plus k over k cubed plus k plus 1. Now, a couple options on calculating this limit. Number one, we have a rational expression here with lead coefficients that have the same power. So this is going to have a horizontal asymptote at 2. The other option is we could use L'Hopital's rule, actually just once, and then or twice. We're going to need to use it twice to get these to cancel, and we're going to see that this limit is 2. It's a non-zero finite number. That tells us that our original diverges because we did the comparison with a divergent series. by the limit comparison test.